Let us talk about this question. We need to design a data structure that supports search, insert, delete, and kth smallest element operations efficiently. Let's understand this with an example. Say we insert these items initially into this data structure. So we have inserted 10, 5, 15, 20, and then 2. So we have done 5 insert operations. Then we do an operation kth smallest for k equal to 3. So our output should be 10. The third smallest element is 10. First smallest is 2, second smallest is 5, third smallest is 10. We can then again do more inserts. Say we insert 1, and after that if we call kth smallest with 3, our output should be 5 because you have inserted one more small element 1. And you can do these operations in any order. You can first do kth smallest, then insert, then delete, and then delete in any order. Now, which data structure you use so that you can perform these operations efficiently? One simple solution is to use array data structure. You can simply put all the items in an array, but if you use array data structure, there will be some operations which will be linear. We have talked about this in the BS3 introduction video. If we use linked list, again there will be some operations will be linear. We have talked about this also in the same video. If we use hashing, with hashing we have these 3 operations in constant time, but this cannot be done in time complexity less than linear, even if we try the best algorithm to find the kth smallest element. With hashing, what we'll have to do is we'll have to copy all the elements into an array and then probably do this median order statistics algorithm on array to find the kth smallest element in linear time. The idea here is to use a binary search tree. If your binary search tree is balanced, or if it's self-balancing, then search, insert, delete can be done in log n time. But how can we find kth smallest element in log n time? That's where this question becomes tricky. See, if you use a simple algorithm to find the kth smallest element, then you can simply do an in-order traversal or iterate over the map in C++ or tree map in Java, and stop when you have iterated k elements and print the element, right? Iteration over map or tree map is like doing an order traversal of the BST. So if you do that, your time complexity of kth smallest element will be big O of k. Now please pause this video and try to think of an approach that works to find kth smallest element also in big O of h time, where h is height of BST. Let us talk about naive approach in detail. In naive approach, let's consider that we have k is equal to 3 and this BST. We simply do an in-order traversal. So when you do an in-order traversal, you begin from 10, right? You increment a count, which indicates how many nodes you have visited, and count is initialized as 0. Once you visit 10, your count becomes 1. Then you come to 20, count becomes 2. Then you come to 40, count becomes 3, which is equal to k. So at this point, you stop, you print this 40, and you are done. Here is pseudocode for the same. It's in-order traversal. This condition is same as in-order traversal. If root is not null, this part is also similar. Recur for the left subtree, process the current node, and then recur for the right subtree. That's what we do in in-order traversal. I have considered count as a global variable. Although it's not a good practice to have global variables, we can pass count as a reference to this function in all the recursive calls. And what we do different from in-order traversal, we increment the count, and if count becomes k, we print the current node. This is kind of pseudocode. Instead of dot, if you are a C++ programmer, you can consider this as arrow, this also as arrow, this also as arrow, and this null as capital null. So this code finds the kth smallest element in big O of n time. Big O of n is an upper bound on the time complexity. You can further optimize it. You can say once you find the kth node, you do not need to process further. You simply need to return at this point. So don't call for the right subtree if you have found the kth node at this point only. Once you do this optimization, your time complexity is reduced to big O of h plus k, where h is height of BST and k is the input, right? Because in the worst case, what will happen? You will go left, 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 which is height, and then you will start processing k nodes and you will stop once you find the kth node. So the worst case time complexity with this optimization becomes big O of h plus k. Now can you optimize it further so that it becomes big O of h? To give you some hint, you can modify the node structure of BST. In node structure, you have key, left and right references. You can add something to this node structure and then you can do this operation in big O of h time. This is called augmented BST. With this augmentation, can you do this kth smallest in big O of h time? Let us now talk about efficient approach. So the idea is to store count of nodes in the left subtree of every node. If you take a look at the C++ structure, I have added this L count and I have initialized this L count as 0. L count is count of nodes in left subtree of this node. In Java, I have also added L count there. I don't need to initialize because Java anyways initializes non-initialized values as 0. So this is the modified node structure we have. And if we have this BST, we are going to have these values in L count. L count for this is 0 because there is nothing on left of it. For this, it is 1. For this, it is 2 because there are 2 nodes in the left subtree of this. For this, it is 4 because there are 4 nodes in left subtree of this. For this, it is 0. For all the leaves, it's always going to be 0. For this node, it's 1 because there is 1 node on the left side. For this, it's going to be 3 because there are 3 nodes in left subtree of this node. So this is what left count means. Let us now see how does this left count helps us in finding the kth smallest element. We do search of the kth smallest element from root, like normal search process. At every node, we follow these steps. For every node, we check if L count plus 1 for this node is equal to k, then this node is the kth smallest element. Let's do an example. Say k is 5, right? And you begin with the root. You notice that 4 plus 1, L count for this node is 4. 4 plus 1 is equal to 5. So this is the 5th smallest element. And how are we getting it? There are 4 nodes in the left subtree which are smaller than this node. So this is the 5th smallest element. So that is how we find the 5th smallest element when we fall in the first case. Now what do we do when L count plus 1 is greater than k? For example, k is 2. So I know for sure this is the 5th smallest element. Second smallest element has to be in the left subtree. So I simply recur for the left subtree or I simply go to the left subtree. So when I go to the left subtree, I check the left count plus 1 for this node is 2 plus 1, 3, which is greater than 2 again. So what we do in this case, we again go to the left subtree. When we come to this left subtree, we see that 1 plus 1, 2 is equal to k. So in this case, we return this 10 and 10 is the second smallest element. Now what do we do when L count plus 1 is smaller than k? For example, I am searching for 7th smallest element in this BST. So when I begin with root, I know this is the 5th smallest element and I want to find out the 7th smallest element. So 7th smallest element has to be in the right subtree. This is something I know for sure, but we need to modify k in this case because we are skipping 5 elements. So what we do is we update the k as k minus L count minus 1. We basically subtract 5 from the k. So if k is 7, what we do at root is we compare L plus 1, L count plus 1 with k. We find it's greater, the k value is greater. So we go to the right subtree, but we reduce the k to 7 minus 5, 2. Because in this subtree, we want to find out the second smallest element. Now when we come here, we again compare L count plus 1 with k. And L count plus 1 is 3 plus 1, 4. And k is 2 now. So when you compare 4 with 2, you see that this is L count plus 1 is greater. So you need to go to the left subtree. When you come to the left subtree, you do not modify k in this case, right? Because you're going to the smaller side. At this point, L count plus 1 is 1 plus 1, 2. And your k here is 2. So you return 70. So your 7th smallest element in this BST is 70. So we have just talked about an approach to find the kth smallest element. What is the time complexity of this approach? We begin with the root. We either go to the left subtree or right subtree. Then again we do the same thing. So it's big O of h. This code is going to be very similar to the search function that we wrote. We can write it either recursive or iterative. In the search function, we were going to the left subtree or right subtree, or we were returning. Here we'll have an extra parameter k, and we'll do these comparisons, and then we'll go to left subtree, right subtree, or return accordingly. Now one question arises, how do we make sure that this L count is being maintained while we are inserting items and deleting items? Now the question arises, how do we maintain L count while we are inserting and deleting nodes? This is really simple. We can always maintain this L count very easily. Suppose I am inserting 35 in this BST. I'll begin with the root. I'll start searching 35 before insertion. That's what we do in the insertion. I'll see that 35 is going to be inserted into the left subtree. So what I'll do, I'll increment the left count for this node because I know that I'm going to insert a node in the left subtree. So I'll make it 5 from 4. Now when I come here, I am inserting 35, it is greater than 20. So I know 35 is not going to be inserted into the left subtree, so I'll not touch L count of this node. Now I'll come to this node, I know that 35 is smaller than 40, so it's going to be inserted into the left subtree, so I'll increment the left count of this as 1. And then I'll insert 35 with initial left count as 0, as we wrote in the constructor. So when we are inserting a node, we can always update and L counts while we search the position where we are going to insert. If the position is in the left subtree, we simply decrement the L count for this node. Otherwise, we do not touch the L count. Same thing can be done with the delete operation, because when you are deleting, you are again searching. So if you are going into the left subtree while searching, you can decrement the L count. If you are going into the right subtree, you don't change the L count.